the second talk of today, given by one of our long-term participants in the program, Professor Martínek, who is going to talk about Bayesian inference.
All right, thanks for a very nice introduction. I'm going to talk about multi-level sequential Monte Carlo type of algorithm. This work is in collaboration with some of my colleagues, with my PhD supervisor Rob Scheichel, and with some of my colleagues from Bath, Julian and Alex. But actually, before I dive into the multi-level sequential Monte Carlo, to the Bayesian inference, I want to present to you a bit of my previous, also multi-level work, but not on Bayesian inference, but on the forward problem. And I'm just gonna try to do this very quickly on 2 slides. Okay. So we are in the standard multi-level Monte Carlo setting, multi-level Monte Carlo for the standard forward UQ, and we are gonna explore inexact computations in multi-level Monte Carlo. The idea is very simple, okay? In multi-level Monte Carlo, you sort of combine the results computed with various sort of model accuracies, and the point is that on the coarser levels in multi-level Monte Carlo, which has been introduced before, the intrinsic model error on coarse levels is quite large. So the main idea is, okay, you probably don't need, when you implement your solver, when you are implementing it actually on the computer, you probably don't need to get the solution very exactly. And this is what I'm going to try to explore and formalize a bit now. So the case study is standard. It has been here mentioned several times, and you're well familiar with that. So it's the standard diffusion problem with a random coefficient. What I do is I discretize it using conforming piecewise linear finite elements on a triangular mesh. And the goal for this case study is to estimate this expected value, which is some smooth functional of the solution. And this has been presented here before. This puts you in the best complexity, in the optimal complexity of multi-level Monte Carlo, which means that the variance decays faster than the cost increases on the levels. We are gonna go deeper in the analysis, like beyond what was introduced here, and we are gonna explore the inexact computations, or the way how to use inexactness in the best way. And what we are gonna assume, and I mean, you have to do some thinking to figure out that this is the correct thing to assume. I'm going to assume that the relative residual computed on level L, so this is the system of linear equations corresponding to the PDE discretization at level L. And I'm going to assume that this is bounded from above by some parameter delta L. And what you can do then is you can propagate the error through the multi-level kind of error analysis, and this is what you end up with. So this should be kind of familiar to you. So normally you would have here in this in these two decay rates just this first part, just this mesh parameter. But now I've propagated how the solution of the linear system comes into play, and now you have also these two additional terms. And the main point is what you wanna do, like what you could do and what you in practice typically do is like you overkill these two guys, like you make them very small and you kind of neglect them. But you don't need to do that. You only need this. You only need to balance them kind of with the discretization error, and that means that you only need to set the computational accuracy on each level like this. So on the finest level, which determines the bias, you need to take your relative residual. This would be the kind of tolerance for the relative residual. You need to take it of this order, and all the other Korsel levels, you have even weaker condition. So the accuracy in terms of relative residual, you need to take of this order, and like these numbers, so that will result in a very kind of relatively high values of delta, which will give you some performance gain. And I'm gonna present one numerical result to you to demonstrate this. So what I have here is basically the standard variance decay in multi-level Monte Carlo, okay? But with a twist, with the added computational accuracy in it. So on the x-axis here I vary the effective precision, so that's the parameter delta L, that's the accuracy with what I compute my solution. And on the y-axis, that's the variance of the multi-level differences that typically is plotted. So the standard plot looks like this. If you take the variance of the quantity of interest on each of the levels, it will stay more or less constant. And if you take the variance of the differences on the levels, it's gonna decay with a certain rate. And here the plot includes the effective precision as well. So one of these curves, let's say the purple curve, corresponds to one particular discretization level. So that's the level 5. So that will be the variance of the differences between levels 5 and 4. If you go with the computation, if you make the computational accuracy very high, then you recover the standard multi-level, Monte Carlo variance decay rates. So that's what you kind of can see here. But the interesting stuff happens when the effective precision, like what if the accuracy of the computed solution is not that high? And here the interesting thing is that if you look at the plot from left to right, on the left hand side of the plot, the computational accuracy of the linear system kind of dominates the overall error, but very quickly as you move to higher accuracy, the discretization error begins to dominate. Yeah, on the coarsest level, this happens very fast. So already for effective precision, like more than 10 to the minus 2, the discretization error of the PDE discretization error begins to dominate. So you probably don't need higher accuracy of your solution than this one, than about 10 to the minus 2. So what you need to do is you just set your stopping criterion for whatever method you are using to about 10 to the minus 2, and this is enough. Like, you don't need to use more. On the higher levels, you can see when the discretization error starts to dominate, when the curve flattens. So as the curve flattens here, the discretization error starts to dominate. Even on the level 4, for example, you don't even need the accuracy 10 to the minus 3. So you can set this comfortably to set this relative residual stopping criterion to about 10 to the minus 3, and you don't need more. And the point is, typically this criterion would be much higher, so that's where the computational gains come from. So this, in much more detail than I presented this now, has been covered in this paper that has been accepted to Scientific Computing, but it's not published yet, so you can have a look in the preprint in the meantime. And now we are actually going to the main topic of the talk, which is my ongoing multi-level work, and we're gonna switch the setting a bit to Bayesian inverse problems, and I'm gonna actually follow up on what Giovanni said here before. So he's done the difficult work for me. He explained all the setup, and I'm gonna have a very easy job now. So the setup is essentially similar as in Giovanni's talk. So the goal is to infer parameters of a kinetic equation. So I just have a different equation. It's some kinetic equation from observed data. And this has many applications. For example, nuclear engineering, radiation therapy, and photoacoustic imaging, which the last one is what some of the people at the German Cancer Research Center in Heidelberg are doing. So that's my main motivation. First, I'm going to describe the forward problem. So if you want to solve an inverse problem, you have to know how to solve a forward problem first. So the forward problem for me is a type of a kinetic equation describing some particle transport. It could be the Boltzmann equation for various types of particles. And there are, in general, kind of on a high level, two approaches to solution approximation of this equation. The first approach, and that's arguably the more standard one, or the one that you might be more familiar with, is deterministic one. By that I mean finite elements, for example. So you have some finite dimensional space that you use to discretize your PDE, and in that space you find your approximate solution. But that's not what I'm gonna focus on now. I'm gonna focus on the second one, and that's I call it stochastic approximation. So that would be a Monte Carlo type of simulations. So what you can kind of do if you want to solve a kinetic equation, the kinetic equation describes some motion of some particles. So what these stochastic approximations do is they basically simulate many of these particles and then average over their trajectories, and that's what gives you approximation of the flow of the particles. And now I'm going to present the Bayesian inverse problem. Again, the setup is basically similar as in the last talk. So we assume that an unknown parameter u is distributed according to a prior distribution, and we observe some data and we assume this about our data. So we assume that the data corresponds to a realization of the true forward map for some ground truth parameter u plus some additive Gaussian noise. So this is what we assume, and then using Bayes' theorem we have the standard posterior distribution of the parameter given the observations like this up to a normalizing constant. So your measured data goes in the likelihood, and here you have the prior here as well. So this can be interpreted as the likelihood updating your prior knowledge on the parameter. Yeah. And as Giovanni said, it's often a good idea to sample from the posterior distribution, and I'm actually gonna use a method which is kind of related to what you heard about in the previous talk. This can be also regarded as an interacting particle type of method. The method that I'm gonna use is sequential Monte Carlo. So the idea of sequential Monte Carlo is this. Or this type of sequential Monte Carlo. I'm gonna introduce a tempering parameter here. The goal now is to construct a sequence of distributions that will transfer you somehow smoothly from the prior to posterior. Yeah. And how I'm gonna construct the sequence in this case is I'm gonna introduce this tempering parameter By varying the tempering parameter, if the tempering parameter is 0, then this has basically, then this guy becomes 1 and you end up with the prior. If this tempering parameter is 1, then you have the full posterior. And by this you can construct a sequence of distributions with that take you smoothly from the prior to the posterior. So this is what I'm going to do, and I'm going to try to sample sequentially from this sequence of distributions, hence sequential Monte Carlo. First I'm going to fix a sequence of tempering parameters. I'm going to sample m particles from the prior, and this is how I'm going to construct my empirical approximation of the posterior. What I'm going to do in a loop is first I'm going to reweight the particles, so they start being distributed according to the prior, and I reweight them according to the first tempered density. Then I resample the particles, which is kind of to multiply the particles with higher weight, so I turn weighted particles back into unweighted particles. That's what this step is doing. And then in these two steps, the particles become correlated, yeah, because you and this is especially a problem in high dimensions, because these two steps then make kind of the particle ensemble often collapse into a small number of particles. So what you want to do then is you kind of decorrelate the particles using a couple of steps of some Markov chain Monte Carlo method. And this is a standard and widely used algorithm, and works for the posterior known up to a normalizing constant, which is what we want. And now I'm gonna go to the sort of crucial part of this talk, which is approximating the forward map in the Bayesian inverse problem. So if the forward map is defined through a solution of a kinetic equation, then you typically can't get exact evaluation of the forward map for your parameter. So what you typically do is you choose some high fidelity approximation, which I denote GS of G, and you sample from this modified, from this slightly wrong posterior distribution, where you just plug your approximation instead of your true forward map. Slightly better, more involved approach is has been explored in this paper, Multilevel Sequential Squared Monte Carlo, where Jonas Latz basically adapts throughout the tempering process, throughout the SMC. He adapts the accuracy of the forward solver here. But in our case, GS, as I mentioned before, is stochastic. It's somehow random. So one thing that we develop can be viewed as a stochastic counterpart of what the authors are doing is in this paper. So we are basically, one thing that we are doing is adapting the accuracy as you progress in the algorithm. So I just want to summarize what the contributions that we are doing are. The goal is to develop an efficient sampling method, SMC, for our problem. And it's very important. We have these three sequential Monte Carlo steps. We reweight, we resample, and we mutate the particles. And we make two contributions to sequential Monte Carlo in this context. We accelerate reweight by using solvers with increasing accuracy throughout the algorithm in a smart way. And we accelerate the mutate step using some fast particle decorrelation, basically using coarse MCMC first, coarse chain, and the fine chain to speed up this sequential Monte Carlo step. So what you can see is that I'm trying to use kind of multi-level techniques. I'm using multi-level techniques, but there is not the telescoping sum is not there anymore. So I'm kind of trying to use multi-level techniques in a different way here. So now we need a bit more of theoretical background. I'm going to try to give you some background on solving the inverse problems if your forward map is stochastic in some sense. So I wanna now formulate the problem informally. So if now the GS, the approximate forward map, oh yeah, the S stands for number of samples. So that would be kind of that would be kind of a parameter that determines how accurate your approximation of the forward map is. So you want, as you take more samples in the forward map, you want it to converge to G, to the actual forward map in some sense. But the question is now, since this GS noisy is random, if you plug it into the likelihood, like what is even this object? Like how can we describe this? And what if, and this is typically the case, the randomness in the noisy approximation depends on you. So I'm gonna give you a bit more of motivation for some abstract definitions that are coming. My toy problem here is given by approximating exponential density by binning. Yeah. So I have some underlying exponential density, and what I can do is I can sort of divide the domain into some bins, and I can take the average of this density over the bins, and that will give me a fixed kind of deterministic approximation of the underlying density, and this is what I'm gonna consider to be my true forward map G for the moment, okay? And now I approximate the exponential density in a stochastic way as follows. I sample from the exponential density, and I bin the samples. I check the samples on the mesh that I have here, and I compute the averages of the samples over the mesh, and that gives me a random approximation of my underlying density. And you can kind of see that the noise structure is like not the same everywhere. Obviously, the noise structure will also depend on what this density looks like, what the black density looks like. For example, if the black density looks like this, if it's kind of like the other way around, then the noise structure will be different. But in general, you can kind of see that you can write the noisy approximation as the true blue G of U plus some mean zero noise conditioned on the parameter U, conditioned on what the density actually looks like. Okay, so this is the motivation. With this motivation in mind, we're gonna go to some abstract definitions now. And I'm just trying to abstract what I mean by stochastic forward solver. Okay, so first I fix some accuracy parameter greater than 0, which would be the number of samples, and I fixed some space where my samples, some abstract space where my samples are gonna live, and I define the noise model as a Markov kernel from the parameter space times some sigma algebra on the noise space to 0, 1. So the important thing is Markov kernels are a tool to define conditional distributions. So what I'm trying to do here, I'm trying to find an abstract way to define how the noise in my stochastic approximation is conditioned on the parameter. Okay, so this determines the noise structure, the raw samples in the abstract sample space conditioned on the parameter u. And then in the second step, I consider a post-processing operator. So as a stochastic solver model, I basically define this map G tilde, which will take the samples, the raw samples from the sample space, and will map them to the observation space. So this map acts as a form of post-processing and maps the raw samples onto the observation space, which could be given by binning, for example. So this map could be binning, for example, or it could be using kernel density estimators or your favorite type of post-processing of the raw samples. And of course, in order for these things to kind of make sense, you want to assume some convergence conditions on this Markov kernel and on the noise model. One of the conditions that you might want to assume is that if you average your if you average the realizations of your post-processing operator over all possible noise combinations, you want to recover the true operator. So that means essentially that this operator, that this stochastic forward solver is unbiased. That would be the interpretation of this assumption here. And now let's see how, using this sort of abstract framework, we can we can analyze what's going on when you use these stochastic forward solvers in Bayesian inverse programs. So I define some marginal measure, marginal approximation of the posterior like this. So I take the likelihood, I plug into the stochastic forward solver, and I average over all possible solver or noise realizations. And this is actually a generalization of something that has been introduced in Arita's paper in a couple of years ago. And I just want to point out that the marginal approximation that I just defined is not going to be typically equal to the true posterior, because the true posterior is given by this. So this is the likelihood that kind of defines the posterior. The prior is the same in both cases. And what you might do is you might plug in the convergence assumption that I had on the last slide, and you would end up with this expression. But like these two expressions obviously are not equal in general. So now basically what I'm trying to say, I've introduced some error in my posterior, and I might want to also quantify how the error kind of behaves. Why? And now I kind of getting to the core of the problem, like why I chose SMC in the first place, and why I think this all fits together kind of well is the reason is basically this picture. So look what happens here. This picture shows what the marginal posterior that I just defined, the marginal approximation of the true posterior, its behavior when the accuracy of the forward solver decreases. Okay. So if your forward solver is infinitely accurate, you recover the true posterior, and then the accuracy of the forward solver gets smaller and smaller, what happens is like you get the kind of tempered version of the posterior, yeah? So what you can observe is the following. The noise in the forward solver, kind of you can interpret it as increased observation noise, and increased observation noise increasing observation noise can be interpreted as a form of tempering. So previously, I basically had the sequential Monte Carlo sampler, which was based on tempering, and the tempering was introduced. By some tempering parameter, which was kind of weighting the likelihood. But here I have a natural kind of form of tempering, which also corresponds to how expensive my evaluation of the likelihood is. Yeah. So the more I go from the yellow posterior to the blue prior, the less accurate my approximation of the posterior is, but the cheaper it also is. So when I saw this, I was like, okay, I want to combine this in a hopefully smart way to get a nice SMC sampler. So the goal is the following. Formally speaking, to construct a sequential Monte Carlo sampler on the extended space, which means parameter space times the noise space, targeting a measure which admits this marginal approximation as its marginal. And this, in a different context, in a slightly different context, has been done before. So this algorithm could be called pseudo-marginal density tempered sequential Monte Carlo for Bayesian inverse problems using a stochastic forward solver with a fixed number of samples S. So this is important now that you fix kind of the accuracy of the forward solver in advance. And what you do is the following. What's in black in this algorithm has been here before, only the stuff that's highlighted here is new, okay? So only the highlighted stuff is new. Now you sample m particles not from the prior, but from probability distribution on the extended space, so it's prior extended by some measure. Then in a loop what you do is you reweight again on the extended space, not just from the tempered kind of density to the second tempered density, but on the extended space. You resample, that stays totally the same, and then you mutate the particles according to a pseudo-marginal Markov chain Monte Carlo. Pseudo-marginal Markov chain Monte Carlo is just a Markov chain Monte Carlo that allows you to sample from the extended measure on the extended space. There is no need to construct the Markov kernel explicitly. This is important because for difficult or for a realistic problem that might be intractable. So the Markov kernel is constructed implicitly kind of by just evaluating your forward solver, your stochastic forward solver. And this is somehow related. This is the context in which this algorithm has been formulated. Bayesian inference in state space models. It's also known as SMC squared, sequential Monte Carlo squared. And now what we want to do is we want to accelerate the algorithm, and I'm going to describe how we are going to do this. So again, what's new is highlighted on the slide. What's black was there before. So now I consider a sequence of accuracies of the forward solver from the least accurate to the most accurate. I sample m particles from the prior extended by the measure corresponding to the least accurate solver. And then I, again in a loop, reweight the particles, basically still using the same, using like a different tempered density, but the same solver accuracy. And then if my solver accuracy has increased in that step, I need to take that into account. So I do one additional important sampling step, which I call exchange important sampling step. Then you resample the particles as before, and you mutate the particles, that stays the same. Okay, so this is how we are accelerating the reweight step, basically. And then there is a theorem, or like, this is of course a very informal version. So we basically verify that what we are doing is consistent, in the sense that this sequence of steps targets ultimately a measure on the extended space which admits the marginal distribution corresponding to the finest solver, to the most accurate solver, as its marginal. It just means you use hierarchy of solvers, but you basically get accuracy of the most accurate solver. That's what it means. But it's not an error estimate. It's just like a consistency type of statement. And in practice, you wanna determine this sequence of samples adaptively. That's a useful thing that you wanna do. And now I'm coming to the second contribution. So that's regarding the mutation step. So an observation that I've made when you run this type of algorithm is that the majority of the cost is actually in the mutation step. So the problem is that with increasing the dimension, the important sampling tends to kind of collapse the particles into small number of particles, and then you need to run kind of long chains to decorrelate them again. This is the issue. And my idea was, okay, and then I was like, okay, how can I use a multi-level approach to basically accelerate this? And I came up with this idea. I'm gonna decorrelate the particles by a cheap approximate chain first, and then use the actual expensive chain to correct for any errors that the cheap chain might introduce. And in our setting, I'm just gonna mention what in my setting the cheap chains are. So the expensive chain is this mentioned before pseudo-marginal MCMC using large number of forward solver samples, and the cheap chain is a different type of kind of pseudo-marginal algorithm, which I'm not gonna go into details there. And it's called Monte Carlo within Metropolis, and it uses smaller number of forward solver samples, so smaller accuracy in the forward solver. And the algorithm now looks like this. Again, only what's highlighted is new. I can basically skip these steps, and what changes is just this mutation step, where I first mutate the particles using the cheap chain, and then I mutate the particles using the expensive chain. And of course, you want to come up with sort of like a smart way how to combine or to set up the lengths of the two chains to get the best possible approximation. So we have some basic convergence results on this in terms of Wasserstein distances between the target posterior and the measure that you start. Full complexity analysis is in progress, but it might be very difficult to obtain a similar complexity result as you have for standard multi-level Monte Carlo, because it's much more difficult to drag the errors throughout as they propagate throughout the algorithm, basically. And now I want to give also some numerical evidence that what I presented is not a complete garbage. So as the first example, I'm gonna I'm going to show you how the reweight step accelerates the algorithm by looking at the heat equation. So my forward operator is given by a bin averaged solution of an initial value problem for heat equation. Namely, it looks like this. So this is the heat equation, this is the initial value, and then at time t, I just average the solution of the heat equation over some bins, and this is my forward operator. Then I simulate I work with simulated data, so I simulate my data by fixing the diffusion coefficient of the heat equation, and I compute a realization or like a true solution corresponding to this diffusion coefficient and add some noise to it. And you can also consider, now I need to sort of define my approximate or stochastic forward solver. So this was the exact solver and now the approximate solver. As the stochastic forward solver, I'm going to use the Euler-Maruyama discretization of certain diffusion process. So the thing is, there is some link between Brownian motion or between diffusion processes and some diffusion PDEs. So you can leverage this link to design a stochastic forward solver or like a stochastic approximation of your true solution. And I'm gonna basically take the corresponding stochastic differential equation, discretize it, sample from the discretization, and then bin the samples at a certain time. So I just want to say straight away that in practice for this problem you never want to do this because first of all you can just, for this particular problem you can compute the solution analytically, but it's just a simple problem that I test my method on to see if it even makes sense to go to more complicated problems. And the results are actually really good. So let me go through the parameters of the simulation. So I fix some true diffusion coefficient, which is just one-dimensional of the heat equation. I fix some end time and number of observations. And on these plots, what I do is I make the posterior more and more concentrated. So I take 20 observations, but with varying observation noise variance. So I start with some quite large noise variance, which means that the posterior will be quite wide. And what I do here is I decrease the noise variance, which means I make the posterior more and more narrow. And I look at the performance of my method compared to the standard sequential Monte Carlo, or the standard kind of pseudo-marginal sequential Monte Carlo in this setup. So on the left-hand side plot, you basically can see that if you look at the mean squared error on the ground truth, so this is the error metric that I choose here, that all the algorithms, like even if you use the exact solution of the heat equation, or you use my algorithm, you basically can't distinguish on this plot between these three errors. But you can see that if you fix number of samples, you get this kind of complexity or this cost of your simulation. But if you adapt the number of samples, if you increase the solver accuracy as you progress through the algorithm, you get the same accuracy, but you get it for a much cheaper price. So this is consistent gain by factor of 5 in terms of runtime actually. So these are some nice first results. On this this reweight contribution, and I wanna also show you some numerical results on the other contribution that I was talking about, and that's the contribution in the mutation step of the SMC. And here I consider, to make it more interesting, a different problem, and the problem is given by the solution of Poisson equation with unknown boundary condition, or that's the inference problem, that the boundary condition is unknown. So what I have here is the Poisson equation in some circular domain, and on the boundary I prescribe a boundary condition, and I parameterize the boundary condition by some parameter, and then I compute a realization, I compute the solution of the Poisson equation for some true value of the fixed true value of the boundary condition, and I add some noise to it again, and that's gonna be my observation data. And again, you can come up with a stochastic way how to solve this problem. Like maybe you don't even know this algorithm. It's quite a cool algorithm. It's called walk on spheres, and it works roughly like this. So if you wanna approximate the solution of the Poisson equation at a certain point, what you can do is you can run Brownian motions or some diffusion processes from that point. You kind of wait until the Brownian motion hits the boundary, and then you can average over these boundary values that you get to approximate the solution of the Poisson equation. This algorithm could actually have some application in practice, because it allows you to because the convergence is actually very fast. You don't need to simulate the Brownian motion like the full path, but you kind of draw circles around your current state, and you can move very far in one step, so you kind of don't need to simulate the whole Brownian motion. And this algorithm could be useful in a situation when you are just interested in the solution in a small number of points. So you don't need to kind of waste resources on approximating your solution on the whole domain, and this is what the tool could be that you could use in that case. So here I give you a bit more detail. So first, this is the parameterization of the boundary condition that I'm considering. So this is now a higher dimensional inverse problem. So in these particular two plots, I'm considering 64 sort of dimensions in the parameter space, and as you see here, like the boundary condition is parameterized by some series, but I try to make the problem quite difficult in some sense. I basically try to make the boundary condition rough. So I set this decay parameter to give me relatively rough function. So this is a relatively slow decay, giving then a rough boundary condition, and it's also like a high dimensional problem. You can kind of see this is the solution corresponding to the ground truth boundary condition, and you can kind of see also here the higher frequencies. And again, because also I said that the walk on spheres you want to use kind of when you don't have that many measurement points, I consider here the case when I have these 20, I think it's 20 measurement points only in these locations. So it's quite a difficult inference problem, because I have a high dimensional problem. but I don't have that many measurement points. So let's have a look at the posterior, what the posterior looks like. So this is like a reference posterior. I just want you basically to be able to visualize what the reference posterior in this problem looks like. So the blue mass, the light blue mass, that's the prior. So this blue mass that's on the picture, that basically corresponds to 95% of the mass of the prior distribution, concentrated around some mean. Yeah. Then I have the ground truth parameter, that's the black rough function. So as you can see, like not you know, such a smooth function. And then I have the posterior mean, or I have the posterior mean, which is this orange curve here, and then I also have the 95% of the mass of the posterior distribution. So what you can see that obviously I don't have many data, so I kind of can't expect to be able to reconstruct these kinks kind of exactly, this rough coefficient exactly, but I have kind of captured quite well the mean. And what's kind of important for me is that these kinks are contained in these confidence intervals. Yeah, so that's kind of what you want from your Bayesian or from your posterior. You want the posterior to not maybe to capture all the fine features of your problem, but at least it should tell you, okay, it's within this confidence interval. Yeah. So this is the problem setup. And now let's have a look at how the method, the accelerating mutation step performs. So what I did actually to sort of like visualize. I got these results yesterday, by the way, or the day before yesterday. So it's really preliminary results, but I think they are quite promising. Well, what I did here, I took the budgeted perspective. Yeah. So I basically said, okay, I want to fix the budget for my mutation step, and I want to see what budget distribution between the coarse and the fine chain gives me the best error. First of all, I simplify because it's when you consider the full sequential Monte Carlo algorithm, it's really difficult to distinguish various error contributions. So what I do here is I simplify the algorithm heavily to just one iteration. So I just do one important sampling step from the prior to the posterior, then resample and then mutate, and just look at this one iteration to be able to isolate the errors well. I look at the error of the posterior distribution in terms of averaged marginal Wasserstein distance from the computed posterior by my method compared to the reference one. Okay, and I use in the sequential Monte Carlo 100 particles in this experiment to approximate my posterior distribution, which is not much, but for a large-scale problem, like you might not have enough resources to go for more, so this is definitely a relevant kind of setup. I should maybe give a bit more details on how I compute this Wasserstein error. So what I do the inference in, let's say, 64 dimensions. I get some sample approximation in those 64 dimensions, and I also have the reference posterior in 64 dimensions, and I compute the 1D Wasserstein distances between the marginal distributions for each of the dimensions and then average them. Okay, so this is what I do. I'm not saying it's the best thing to do, or I'm not saying it gives you the complete information, because it kind of doesn't capture all the correlations, but it's just computationally feasible, and it's hopefully a reasonable error metric. And this is the result, okay? So what I do on this plot is, on the x-axis I fix budget for the mutation step. So I go from fairly low budgets to high budgets, and on the y step, on the y-axis I plot the fraction spent on course level, fraction of the budget spent on the course level yielding the optimal error. Okay, so how should you run first course chain and the fine chain, and I'm asking what's the optimal distribution of your budget between the course chain and the fine chain giving you the best error. This is the question that I'm asking. If you are interested in how I know where the optimum is, the answer is just like I brute force it. I compute all the possible budget, many of the budget allocations, and I just look at which one gives the best error. So there is nothing fancy behind that. And I also varied the dimension of the problem, and you can see very interesting stuff here. So let's start from the low dimension. The lowest dimension I consider is 8, so that's a fairly low dimensional problem. In low dimensions, this plot tells you if your budget is small, you should spend at least you should spend some of it. You should spend about 25% of it on the course level. The rest you should spend on the fine level. And as your budget gets higher and higher, it basically tells you, okay, there is no need to spend anything on the course level at all, like the fine level is basically enough. But the interesting stuff happens when you go to high dimensions. So let's have a look at this curve that's in 128 dimensions. So that's where the kind of curse of dimensionality really kicks in. And the important sampling, like basically really collapses into very few number of particles. And here this basically tells you, if your budget is small, you should spend considerable amount of your budget on the course level first. And then if you have bigger and bigger budgets, then it kind of the coarser chain becomes less and less relevant, because the fine chain itself is able to decorrelate the particles quite well. And like this effect is like more and more pronounced the bigger the dimension is, but it never tells you should spend like everything, all your budget on the course level. Like you can see that there is like a clear threshold about like 70%. This plot never tells you to spend more than about 70% of your budget on the course level. Like you will always benefit from doing at least some number of steps on the fine level. And now I should be quite quick. So now I wanna give you at least an hint about regarding what the error looks like, and I haven't been able to like interpret this plot fully myself, because I got it yesterday from the data. But what you can clearly see, so this is the actual error in terms of the Wasserstein distance. This is the budget, and I fixed the dimension on 64. So that's this curve, and you see that if I use the optimal budget allocation for all budgets, I have basically some error threshold here below which I can't get. If I use only the fine chain, I start from some higher error, and you can tell it will take me a long time until I get to the same error level. So basically, I get the same error for much lower cost, but the full interpretation kind of or the full analysis is not there yet. And this is just a summary of what I've done. We are basically What we are doing mostly now is we are working on the complexity analysis, and we are applying it to some more problems with some colleagues, because it looks like it's working really well. And then that's it from my side. Thank you for your attention.